All right, hello, and welcome to lesson 12.2 on arithmetic and geometric sequences. This is our introduction to sequences, and I'm so excited. You may have seen this in maybe a little bit in middle school, I'm not sure. You should have seen it in Algebra 1, but I don't know. It kind of depends on your Algebra 1 teacher. A lot of times, Algebra 1 teachers are so focused on trying to get through all the state standards, and sequences aren't a huge state standard. They're not a huge test item. So a lot of teachers kind of gloss over it, skim over it, blah, blah, blah. And they're really supposed to kind of teach it. And hey, look, I'm guilty of this myself. I spent maybe a day on this in my own Algebra 1 class, so I'm no better. We're all in here, right? We're all guilty. If your Algebra 1 teacher did spend some time on this, it might just be some review for you. If not, it might be new. But whatever way, we're starting from the ground up with sequences to get us prepared for series, which is more of the Algebra 2 topic. So anyway. So the exploration is up here. It says, for each sequence of numbers, identify the pattern and write the next three numbers that fit the sequence. I'm not going to do that here because this is an exploration, and I think you can figure it out. If you need a hint, that first one, 4 plus 7 gets 11. 7 plus 7 gets 8. 8 plus 7 gets 25. So the pattern is, 25 plus 7 is 32. Plus 7 is 39. Plus 7 is 46. Okay? I'm only doing that one, though, because it's the easy one, and you can figure out the rest. Okay? Alrighty. Let's move on. So what is a sequence, right? A sequence is a set of numbers that follow a particular pattern. Each number in the set is called a term of the sequence. So for example, the sequence 5, 7, 9, 11, the first term of the sequence is 5, the second term is 7, and so forth. So before I continue, I want to get you a little quick familiar with the notation. So I'm going to use a sub n. Now, my pre-cal teacher would say this, assuming we knew what that meant. What I'm saying, if you're not sure, is a sub n means a subscript n, where n is below a. It's the little. It's like a superscript is above. It's like an exponent. Subscript is below. I mean, maybe you knew that, maybe you didn't. It's just a reminder. I felt embarrassed to ask in my pre-cal class when he was saying that. And I don't want you to feel embarrassed whether you know it or not, So anyway, this is a sub n, and it might represent a sequence. So like the sequence here I have is 5, 7, 9, 11. Notice I use curly brackets because it's a set of numbers, right? So what the heck is that in, right? What the heck does that mean? Well, in it's called an index, and often you'll see different letters used for the index. N is one of them. You might see I, you might see K. Those are the most common ones. You'll see A sub I, pretty common, A sub K, and it won't always be A. Sometimes it'll be like S sub I or T sub K, right? It doesn't matter, okay? The choice of letter is kind of arbitrary. I'm just kind of letting you know what letters you might expect. But anyway, all that little subscript means is which term of the sequence. So like we said that the first term of the sequence is 5, right? Well, 5 we call A sub 1 because it's the first term. 7 we call A sub 2, 9 we call A sub 3, and so forth, right? And this goes ... all the way to A sub n. I don't know what n is because, well, this sequence looks infinite, right? It goes on forever. So whatever n is, that's where I would stop. Okay? So that's the sort of notation. So you get familiar with, all that little subscript tells you is the term you're talking about. Okay. Now, it's helpful to think of sequences as functions, where your input of the function is the term of the sequence, and the output is the corresponding value in the sequence. So, for instance, if you make a table, right, like x and y, so I'll make x and I'll make y, right? Then x, is the first. X is the first term, and then the second term, and then the third term, and then the fourth term, and so on, right? And the first term is 5, and the second term is 7, and the third term is 9, and the fourth term is 11, right? But we don't use x and y because we're talking about sequences in particular. Well, the term is given by n, whatever n is. That's the index. And then the value of the sequence is called a sub n. So this is like your x, and this is like your y. Okay? Hopefully that clears things up. Think of it like functions. So a definition. A sequence is a function whose domain is the set of natural numbers, which are term numbers, and whose range is the set of term values. Yes. So, the domain is a set of natural numbers means it's just counting numbers. 1, 2, 3, 4, 5, and so on, right? Now, you could probably expand this definition. You technically could go backwards into the negatives, but you typically, I guess you don't, usually. I mean, you could, but yeah. To write a formula for a sequence, what the goal is to find a relationship between the term number n and the term value a sub n. And then this formula is going to help you find the nth term, right? So like, I might be able to see this pattern. I say 5, 7, 9, 11. I could do 13. I could do 15 and so forth because I see what the pattern is, right? But what if I asked you, what's the 100th term in the sequence? Well, are you going to write this out 100 times, right? 11, 13, 5, 15, 17, 19, 21, and so forth. You're not going to do that, right? The goal is to find a sort of formula that would tell you what that number is, okay, depending on what the term is. Okay. And this should start out pretty easy, but this can be a very difficult thing. It really is a skill to develop in math, is how to formulate a sequence. But we are starting off easy, okay? So here we go. Example 1, let's write an explicit formula for the sequence a sub n equals -2, 1, 4, 7, and we want to predict the 20th term of the sequence, okay? So what's happening here? Well, I'm going to make a table. Here's n, and then here's a sub n. And I don't like that that's not a straight line. Let's make that a straight line. Okay. So the first term is -2. The second term is 1. The third term is 4. And the fourth term is 7. And I might see, okay, hold on. So from 2 to 1, and then from 1 to 3, and 4 to 7, is there a pattern there? It should be sticking out to you that I'm adding 3 every time, right? Adding 3 every time. So I might make a prediction. The fifth term should be 10. And if this prediction is right, then I could keep going. I could find the 20th term of the sequence. But I don't want to write out 20 of these, right? I need to find a formula for it, right? Well, let's see what happens. So I'm going to write it like this. A sub 1 is, we said that was -2. And then we said a sub 2, yeah, okay, look, we said that's 1, but if you think about it, how did we get 1, right? Well, we took the original number, -2, and we added 3, right? And that got us 1. Okay. And then if I look at the next term, a sub 3, I said, well, okay, well, that's the last number. It's the 1 and then plus 3, right? But what I might encourage you to do here is really look at that first term and see if you can make a comparison from the first term to later terms, right? So I say, okay, well, it was -2. I added 3 to get a sub 2, right? Because that's right there is a sub 2, and then I'm adding another 3, right? So really what I'm doing here is -2 plus 2 3s, which I might say that's 3 times 2. And I can carry that idea on to the next one. A sub 4 is -2 plus, right, it's going to be 3 times 3. Because again, it's -2 plus 3 times 2. That's a sub 3. To get a sub 4, I need to add 3 to that, so I'm adding another 3. So that's just -2 plus 3 times 3. And now I say, why is he writing it this way? Well, I'm writing it this way because you should start to notice a pattern here, right? -2 seems a constant value in here. And then there's something about 3. 3 looks constant too. What's changing? Well, I see a 2 here, I see a 3 here. What is 3 getting multiplied by in a sub 2? Well, it's 1, right? And if I go back one more, well, there's nothing there, but wouldn't that be 3 times 0? I think it would, right? Now, what do these all have in common? They all have a -2, and they all have that 3. So what's changing? This, right? The 0, the 1, the 2, the 3. And so what you want to do is make a comparison about these numbers. How do those relate to these subscripts? Well, 1 to 0, well, 0 is 1 less than 1. 2 to 1, well, that's 1 less than 2. 2 is 1 less than 3, and so forth, right? 3 is less than 4. So I'm going to backtrack all that. So if I were to generalize this, right, what would a sub n be? A sub n. Well, this -2 seems constant, and so does this 3. But what's the number here, right? Well, it looks like I'm taking the subscript, and then I'm subtracting 1 from it. And so if my subscript here is n, then what am I subtracting? I'm doing the subscript n minus 1. And this would sort of be our formula, right? Because now I can plug in any number for n, right, to make sure this works. And to show you that it does, right, what is a sub 5? Well, it's -2 plus 3 times 5 minus 1. That's -2 plus 3 times 4. That's -2 plus 12, which equals 10. And 10 is what we have over there. So, yeah, it works. So we should say with confidence, a sub 20 is -2 plus 3 times 20 minus 1. So that's -2 plus 3 times 19. And I already went ahead and made a lot of the calculations here. You should get 55. I didn't want to waste time in the video like calculating a lot of stuff, so you should get 25. That's 55. And that's kind of how you write an explicit formula. I will tell you, it's not the same pattern every time. Your goal and what makes this difficult is playing around with the terms to find a pattern. I didn't have to write it this way, right? I just kind of chose to, and then a pattern emerged from it. So you will have to really some of these you'll really have to experiment. So I'm going to move on to example 2, but I do encourage you, can you try and find an explicit formula for this sequence? And by the way, this is nearing the level of calculus difficulty. We're not doing really any calculus here yet, but sequences are a huge part of calculus, especially the end part of it. And creating a sequence is a really major skill. So I do challenge you. I want you to pause the video and try this one and see if you can get it before I do it. Okay. So let's write an explicit formula for this sequence, right? I'm gonna make that table. The table might help you out, all right? And I do want to let you know, you're not always looking for differences. You're just looking for patterns. So my first term is a half. My second term is 4/3. My third term is 9/4. And my fourth term is 16/5. So, what's happening here? What's the pattern? So a sub 1 is 1 divided by 2. And a sub 2 is 4 divided by 3. So what comparisons can I be making here? Maybe I'll go to the third one. Usually 3 terms should be enough to figure out a pattern, but you might need more. You might. You might need 4 or 5 terms. What can I find here? Well, I'm going to look at some of the sequence of these numbers. Look at the numerators. 1, 4, 9. And then, of course, that next one is 16. Now, that's a familiar pattern, right? 1, 4, 9, 16. You ask yourself, well, what else do I have in common? That's 1 squared, that's 2 squared, that's 3 squared, that's 4 squared. So I do know I could write this as 1 squared over something. I could write this as 2 squared over something. I could write this as 3 squared over something. And what I'm doing here is I'm drawing a connection between the subscript 1 and then this number, 2 and then this number, 3 and then this number. So it looks like the numerator appears to be whatever my subscript is squared. Okay. Well, now let's look at the denominator. I look at 2 and I compare that to 1. Look at 3, and I compare that to 2. I look at 4, and I compare that to 3. And I can go further, 5, compare that to 4. What do they have in common? Well, how did I get 2? I did the subscript 1 plus 1. How did I get 3? I did 2 plus 1. I did 3 plus 1 to get 4. And so maybe you're starting to see a pattern emerge here, right? We found out that the subscript is getting squared on the top, and on the bottom, it's the subscript plus 1. So let's generalize this for a sub n. Well, the top would be the subscript n squared divided by whatever that index n is plus 1. And that is the sequence. So what is the 7th term? A sub 7. Well, assuming it follows this, it would be 7 squared over 7 plus 1, which we know equals 49 over 8. And that is the pattern. And do you see how there was nothing to do with, like, arithmetic here, all right? Meaning, adding numbers or subtracting numbers, right? It was just pure, it was just looking at the numbers and thinking about them. So it's kind of a difficult skill to teach, because how do you teach pattern recognition? Well, you just do a bunch of problems until you start to see patterns. Okay, so here we go. Arithmetic and geometric sequences. So what are these things, right? Because that's the title of the lesson. So an arithmetic sequence is a sequence in which one term equals a constant, in which one term equals a constant added to the preceding term. So that example we started off with on the previous page, 4, 11, right? 4, 11, 18, 25. You're adding 7 every single time, right? So because you're adding a constant term to the preceding term, this would be known as an arithmetic sequence. The constant, this plus 7, right? This constant is called a common difference. And we will denote the common difference with the letter D for difference. By the way, why is he saying arithmetic rather than arithmetic, right? Arithmetic versus arithmetic. Okay. One's a noun, one's like a verb or an adjective or whatever it is. I don't remember the English stuff. Arithmetic, right, is like, I don't want to explain it. There's a context, all right? I can't remember the linguistic whatever. I know when to call which one which, but like, are you good at arithmetic? Can you add numbers, right? Versus if you're describing something. So I think arithmetic is the adjective, and I think arithmetic is the noun. I think that's right. Like, are you good at arithmetic? Yes. Would you say, are you good at arithmetic? No. Would you say an arithmetic sequence? No, absolutely not. It's an arithmetic sequence. It describes what type of sequence it is. Sorry, turning into a linguist here, but I want you to know why these words are pronounced differently. It's an English thing. Anyway, a geometric sequence is a sequence in which a term equals a constant not added, but multiplied by the preceding term. In hindsight, I probably should have made this second example a geometric, because example 1 is arithmetic, but example 2 is not geometric. I probably should have done that. Here's a quick example. 2 times 5 is 10, times 5 is 50, times 5 is 250. Yeah, you see that, right? Times 5. Okay, that's a geometric sequence. This constant multiplier is called a common ratio, which we'll denote with the letter R for ratio. Okay. And all we've got here is, 2 more examples. Okay. So determine whether the sequence is arithmetic, geometric, or neither, and give a rule or formula for the composition. And then calculate a sub 100. Okay. So you look at your sequence here, right? You can make a table. I'm just going to jump straight ahead, right? Look, 3 plus 7 plus 7 plus 7 plus 7, right? That's the common difference here. So I know that it's arithmetic because D equals 7, right? There's a common difference of 7. And so I can write it like this, right? I can say the first term, a sub 1, is 3. And the second term is the first term, 3 plus 7. The third term is 3 plus 7 times 2. And as I'm following kind of a similar pattern like I did in that previous problem, in example 1 of the other page, right? A4 is 3 plus 7 times 3. Because I'm just adding 7 each time, right? So this is like 7 times 1, and this is like 7 times 0. So from here, you should be able to formulate a sub n. A sub n is going to be the initial number 3 plus 7 is the difference times, it's that same comparison. This isn't really new. 1 and 0, 2 and 1, 3 and 2. All of those multipliers are 1 less than the index n. And by the way, if you want to distribute this and stuff, you totally can. I mean, I would. 7n minus 7, so therefore, right? Therefore, a sub n equals 7n. 3 minus 7 is negative 4. So that's actually my sequence here. You don't have to write it like that, but you can. I like to write it like this. You know, if I have like terms, I like to combine them. And then let's calculate a sub 100. Well, I have my formula, right? 7 times 100 is n minus 4. So it's 700 minus 4, which is 696. 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 Boom. Got it. And that's an arithmetic sequence. It's pretty much, yeah. I was going to leave that one for in class for everybody to explore on their own, but I just kind of shot through it. So I do challenge you to try example 2 here. Determine whether the sequence is arithmetic, geometric, or neither, and then give a rule for its composition. Because we're not in class, I mean, you can pause the video, try it, but I'm just going to go through it. 3 to 6, 6 to 12, 12 to 24. Now, you might try, I would always try a common difference first to see if there's a pattern. 3 to 6, well, that's plus 3. 12 to 6 to 12, that's plus 6. 12 to 24, that's plus 12, and then plus 24, and so forth. Those aren't common differences, right? However, if I think in the lens of multiplication, 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48, and that works. So, a sub 1 is 3. We know this, right? Both these sequences start at 3. So what is a sub 2? A sub 2 is 3 times 2. A sub 3, right, is 3 times 2, because that's the previous term, 3 times 2, times 2, right? Well, that's 3 times 2 times 2, right? So that's 3 times 2 squared. And then a sub 4, well, that's 3 times 2 squared times another 2. Well, okay, 2 squared times 2, that's 2 cubed. Oh, hold on a second here. 2 cubed. So what am I seeing here, right? Well, that's 2 to the 1. Does it make sense if this is 2 to the 0? Absolutely it does, right? Because 2 to the 0 is 1, so 3 times 1 is still 3. And so I see from here, I should see a pattern. A sub n is the initial number 3 times, looks like I've got a base of 2, and what's changing every time is the exponent. And actually, exponent is changing just like the common difference was n minus 1. And so that's my formula there. 3 times 2 to the n minus 1. And so I want to calculate a sub 15. Right, I can box this. This is good. You can box this. A sub 15, well, that's 3 times 2 to the 15 minus 1. That's 3 times 2 to the 14. And I don't know what 2 to the 14 is on top of my head, so this is a calculator thing. We figure out that a sub 15 is 49,152. Let me box it and call it a day. Beautiful. Okay. And that's arithmetic and geometric sequences. So there you go. Conclusion. So actually, there is a reason I wrote all this like this. And maybe you found this throughout doing this. Any arithmetic sequence, you can write like this. Okay. The a sub n term is the initial plus whatever your common difference is times n minus 1. And it's always going to be the first term and n minus 1, and then whatever the common difference is. For a geometric sequence, you're going to multiply by the n minus 1 common ratios. So it's the first term times r is the common ratio with the exponent is that n minus 1. And that n minus 1 is the relationship with the index, with the term number. And yeah, that's it. That's this lesson. I think that was short, although I don't actually know. So there you go. Arithmetic and geometric sequences. Hope you enjoyed. Have a good night, and I'll see you in the next video.